Okay, well, um, great. We're gonna review partial fraction decomposition. It's really important to understand how to do partial fraction composition, because if we look at the Laplace transform table, what we see are certain forms that we want to be able to match. So we see things like 1 over, or I guess a over s squared plus a squared. We see 1 over s minus a. That's going to be a common one. We see b over s minus a squared plus b squared, etc. So we want to make sure, well, one of the things we notice about all of these is that these are single factors on the bottom. We can't factor these out anymore. Can't factor anymore. So if you get something where you have two factors multiplied by each other, you want to be able to break them down into a way that you can deal with on the table, and that's using partial fraction decomposition. So let's go through some examples, because there's a few different cases. So let's say we have s plus 9 over s squared minus 2s minus 3. We want to focus on the denominator. The numerator doesn't matter super much. We're going to still deal with it, but in terms of figuring out how to factor this, it's not going to matter. So we can factor this one. This is the simplest case, I'll say. Simplest case. So here we're able to factor this into s plus 1 times s minus 3. And right now we can notice that the factors are different, and they're all linear, meaning there's no squares, there's no cubes, or anything like that. So what we can do is we can say, well, this is going to be a, where a is unknown, over s plus 1, one of the factors, plus b over the second factor. And now we need to find a and b. And notice how, when I'm looking at what I want as an output, something over s plus 1, something over s minus 3, that's specifically one of these factors on our Laplace transform table. So what we do here is first, we want to get rid of all the fractions so we can multiply through by common denominator. And if I do that, this simplifies. Great. All right. And now at this point, we could do a few things. There's two methods here. You're welcome to do whatever you want to do to find A and B. There's the coefficient method, where you match coefficients of powers of S, similar to how we did that in our second order linear differential equations, where we matched coefficients for powers of t. There's also the substitution method, and I like this one better. If you don't like this one and you'd rather use the other one, that's fine. You can ask me questions on how to do that. But for the example right now, I'm just going to do the substitution method. So what we do is we pick an S to make one factor 0 and solve for the remaining coefficient. In this case, we can see if I pick s equals 3, then I get 3 plus 9, I'm just going to plug it in, equals a. 3 minus 3, that's the factor of 0 that I want, plus b, 3 plus 1. And now we can see that it's very easy to solve for b because there's no a, and we can just divide in that case, and b equals 3. Great. So now we go back to the original expression, and we want to pick another s value that makes a different one equal to 0. So in this case, if I pick s equals -1, then we can see how that's going to make this factor here 0. So let's go ahead and do that. Get -1 plus 9 equals a, which is still unknown, -1 minus 3, plus b, -1 plus 1. So we can see that is 0 like we like. And then we get 8 equals -4a, and a equals -2. Great. We have solved for a and b, and now we know that our original fraction, which was s plus 9 over s squared minus 2s minus 3, equals -2 over s plus 1 and plus 3 over s minus 2 minus 3. There we go. So we have used partial fraction decomposition to break this up, and now we have things on our table. But unfortunately, it's not always as easy as this. So let's do another one. Let's do a second example where, and this time we have example where we have a higher term in the denominator. So higher term of s in the denominator. Well, what do I mean by that? If we had something of the form 2s squared plus s plus 13, the numerator again doesn't matter here. But let's say the denominator we factored s minus 1, but then we had s plus 1 squared plus 4. Now it's factored specifically that way because if I look at this, well, this matches something in my denominator up here. So that's the reason why it's factored specifically like this, but you might not see it that way. And I'll post another video about how to get it in that form. But you could see something that's like s squared plus, I guess this would be 2s plus 5. So if I multiply that out and add the 4, I will get this sort of polynomial where I can't really factor it into two factors multiplied together. This ended up being like, we get from this to this by completing the square, which I'll talk about later. But let's say we're at this point where we can't factor it any further. It doesn't need to be in this completed the square form to use this method, but we just want to note that this is factored as much as possible. But still has an s squared. So we treat it the same way. Well, in a similar way. We have A over S minus 1. That's all the same. But now for our second term, because the numerator has an S squared, what we want to do in the denominator is have one power lower. So because the denominator has S squared as highest power, the numerator needs one power lower. So that's that BS plus, we have an S squared and we have this BS term that we didn't have on the other side. Once we get it into this form, everything else is pretty much the same. So similar way to solve. Let's go through and do that. And notice how, again, this numerator really doesn't matter here. I'm not doing anything special with it just because there's a squared in there. This one could have not had a squared. It doesn't really matter. What really matters is what's on the denominator. All right, so let's pick. I'm going to pick S equals 1. That seems to be a pretty obvious one here. And then I get 2 times S squared plus 1 plus 13 equals A. 1 plus 1 is 2 squared plus 4 plus, and this is technically B, S. So B times 1 plus C. And now we have 1 minus 1. So great, that goes away. Let's do some simplification. 2 plus 1 plus 13. I'm just going to add that all together. So that's 3 plus 13, that's 16. If I'm doing things correctly. Then we have 4 plus 4 is 8. All right, that's pretty nice. So we get A equals 2. So now one of the issues is once we've gotten this, there's not really a good way of getting other factors to go away. One of the obvious things might be we can get the B to go away by picking S equals 0. So let's do that. S equals 0 is usually a good one because it gets rid of a lot of terms. Even if it's not obvious that S equals 0 is going to be something that works out nicely. We still have to deal with what's going on with A, but that's okay because we know what A is now. Okay, so my B is gone. I'm going to plug in, well, this is 13. I'm going to plug in what A equals. A equals 2. Then I get 1 squared is 1 plus 4 is 5. Great. And then what we are left with is minus C. Okay, so we have 10. I can subtract 10 from both sides. And I get C is minus 3. So we have 2 so far. For the third choice, you can really use anything you want. I'm going to go ahead and use S equals minus 1 because since I'm squaring things, I want to keep the numbers relatively small. And minus 1 is a good option for that since I've already used 1. But also, I do see that there is an S plus 1, right? So I have A. Then I have S plus 1. And while this isn't going to get rid of my A like we did with our first example, I do know what A is already. So I can plug that in. It's still simplifying a little bit, so that's pretty nice. Oops. Yeah, -1, great, plus C. All of this, and this was -1, -1. All right, let's go through this carefully. We get -1 squared is 1 times 2, -1 plus 13. I'm going to just take care of the left-hand side for now. So that gives us 12 plus 2 is 14. Great. A, we said was 2. 2 times 4, because this term goes away. And this is 8. And now we get, and make sure to be careful about our parentheses. We want to make sure that we don't miss anything. This is minus B plus C. And if I distribute that and plug in plus C, which is -3, so I get -2 minus B. That's going to be plus 2B. And then I get -2 times C, but C is -3, so this is plus 6. Okay, great. So what do we end up getting here? 12 plus 6 is 14 actually, so we get 0 equals 2B, and B equals 0. Doesn't always work out where B equals 0. It worked out in this case, but that just is how it ended up happening. You still need to include that term, even though in this particular set of numbers that we worked through, it ended up not mattering. So just because we got 0 here doesn't mean it's always going to be 0. So plugging things back in, this was our A over S -1, and then we had plus B, which was 0, 0 times S, -3 over that large term we had, S plus 1 squared plus 4. So if you wanted to simplify this slightly more, we have S 2 over S -1 -3 over S plus 1 squared plus 4. And that is how we have broken up this one. So the last example that typically comes up is repeated roots. Let's do a repeated root example. I don't have one ready, but I can pull one up. I want to do one that the answer is kind of nice, not too messy, so I don't want to make it up on the spot. Otherwise it could be something with a bunch of ugly numbers in it. Let's see. Yeah, sure, we can. That looks messy. That's fine. We could do this one. So let's do example repeated roots. So let's say you have x squared plus x plus 1 all over x plus 1 cubed. Now again, we need to break this up because we don't have anything raised cube in our list of Laplace transforms. So what we need to do here though is it's going to be a over x plus 1 plus b over x plus 1 squared plus c over x plus 1 cubed. We have to build up factors in the denominator. So we can't just go straight into that last factor. We have to build them up. So now let's go through this the same exact way. Honestly, at this point, if you wanted to stop the video, I don't think I'm going to be doing much else for this, but it's the same process that we did above. We multiply through by the common denominator. Okay. In this example here, maybe you want to multiply things out and do the other method. If you want, I can do that one right now. If we wanted to do I said before that there was two methods. Where is it? There was the substitution method, which I've used already twice, and then there's the coefficient method. So I'll use the coefficient method. Let's do via coefficient method. So you can see what that one is like and then pick your favorite, but they would be the same thing. I mean, notice here though, like I could pick, I don't know why I did X's, but fine, X's. Notice here that I could pick X equals -1, but then after I pick X equals -1, I'm not going to be able to pick another value that makes a 0 anywhere. So that's why the coefficient method might be useful. So what we can do is we can multiply things out. So first we multiply out x's or s's, it doesn't really matter. A x squared plus 2 ax plus a plus b x plus b plus c. So I've multiplied everything out. And then what I'm going to do is, I mean, honestly, before we even get to this, I'm going to use both methods. I'm going to use both methods because it's going to actually be easy. Let's get the C first. Get C. Oops. Get C. Why is this doing this? We're going to first get C by the substitution method. And the reason for that is because it's actually going to get it's going to be really easy to do with making zeros. So if I set, well, I want to do my s's here. So if I set x equal to -1, I get -1 squared -1 plus 1, and we get a -1 plus 1 squared. That goes to 0 plus b -1 plus 1. That also goes to 0. And we're left with C. So we can see that those cross out as well, and that C is 1. So that's one less thing to worry about. So you can use both methods. You can mix and match. So now going to multiply out and plug in C. Great. And we want to match. I bet this doesn't happen in class, but I don't know why it happens at all. Match coefficients. I think it just might be how I'm writing on the tablet. Match coefficients of the same order of x. So we want to make sure we match those. So what do I mean by that? Well, we have x squared and ax squared. Right? Those are the only ones that have an x squared in it. We have x here, we have 2ax, and we have bx. And I'll leave some room so I can solve some things. Okay. And finally, we have 1a, b, and that was our c. So 1 equals a plus b plus 1. So right now, a is really easy to solve. So I can get 1 equals a from that, right? If x squared, then 1 has to equal a. The last one we could use, doesn't matter which one you want to use here. Yeah, let's use this one at this point. At this point, we kind of have a redundancy because we use that other method. If we didn't use that other method, we'd have to use all 3 equations, but that's okay. right? We made our lives a little bit easier. So this is -1 equals b. And we already know what c is. So if we go back up to what our equation was, now we know that with repeated roots, I will have a equals 1 plus b, I guess, -1, and then plus c, which was also 1. So now you should know how to handle any partial fraction decomposition.